Hello, welcome to Storage Developer Conference 2020. My name is Amarjit Singh. Today I'll be talking about leveraging modern networks to deliver faster storage to database workloads in Kubernetes. So a little bit about me. I work for a company called Kioxia America, which is a new name for Toshiba Memory America. I run a solutions engineering team in Kioxia America. My interests are in cloud and especially in Kubernetes. So you can reach me at my Twitter handle, Amarjit S. So today's talk, let's see what is our agenda, what are we going to talk about. First, I will talk about what is going on in storage technologies, especially how storage technologies are evolving towards NVMe. Then I will talk about what's going on in networking technologies. Then we will discuss what type of workloads are there in cloud, especially in Kubernetes. And then we'll focus on stateful applications. And I'll talk about them, what they are. Then we will see how local storage versus network storage has their benefits and can be used in cloud technologies such as Kubernetes. Then we will blend everything together and then see how storage technologies, networking technologies, and modern cloud orchestration framework such as Kubernetes, they are playing together. Towards the end, I will have a live demo, and then we'll also talk about what is the future and what are the takeaways from this session. So first of all, let's talk about what is going on in storage technologies. This is a storage focused conference, so I am lucky not to be basically worried too much about spending a lot of time on explaining storage technologies, but let's refresh our minds. So in storage, when we talk about storage, the end piece in the storage is the media where data gets stored. How data comes to that media is another important piece. And then which methods, which protocols are used to bring data or bits or bytes all the way to the storage media is done through protocols. And one of the very popular protocol is a SCSI. So SCSI was invented in 1986 when we had popular mainframes or large computers. And then with time, a lot evolved. We saw how .com gave birth to basically distributed computing or computing in silos. And then now we are in the age where public cloud is the talk. So everyone has either moved into cloud or has plans to move into cloud. So between now and the time SCSI protocol was invented, a lot has changed the way we run infrastructure, but not much has changed the way we store data. So after 1986, the next change in storage protocol was in 2011 when NVMe protocol was introduced. So NVMe originally was basically, NVMe was invented or built to store data on flash drives. Before that, even the flash media was present, but protocol used to store data on flash drives was still SCSI. Then there are other relevant technologies such as RoCE version 2, which is basically RDMA over converged Ethernet, that came into picture in 2014. Then NVMe over Fabric, sending NVMe protocol commands over network, was introduced in 2016. And then in 2016, Linux kernel started native support for NVMe over Fabric, initially for RDMA protocol transport, but later in 2019 with kernel 5, which introduced native support for TCP to carry NVMe over Fabric commands. So let's see how disk drives evolved over time. Uh, when media was spinning magnetic, and then protocol to bring data to media was SCSI. That time we used to call HDD, we still call them HDD, hard disk drives. So then media changed from spinning to flash, but the protocol was still same to bring data to the media, which was SCSI or SATA. Those protocols, they were originally built to store data on spinning medias, magnetic medias, but we still started using them to store on flash. That was not what it was optimized for. Then the evolution took us to NVMe protocol, which is built to store data on flash drives. So we'll talk about benefits and how this NVMe protocol fits in our modern clouds. If you look at the performance of these three technologies, when it was hard drive, media was magnetic and protocol was SCSI. At that time, we were happy with one type of performance, but then when media got changed to flash drive with SSDs, but protocol was still SCSI, we got a huge jump in performance. But when we changed the protocol, even the jump was much, much bigger. Now we have enormous performance from NVMe drives. In fact, many of our applications are still not ready to leverage that performance. We'll talk about that. So one of the reasons that we got such a huge jump in performance with the invent of NVMe is NVMe basically it optimizes how data is brought from application layer to the end media when it travels through kernel. So it basically either optimizes or bypasses a lot of layers, especially block layers, which otherwise were used by the earlier protocols. So let's take a quick look at how NVMe is different from SCSI. So SCSI has one queue to carry storage commands. NVMe on the other side has 64,000 queues. So if you put one queue for one core in a client, still that's such a large number. That's a lot of queues. So next, each queue in storage was capable of carrying 64 commands at a time, but NVMe can do 64,000 commands. That's a difference. So altogether, we used to get around 12 Gbps of throughput in SCSI, but in NVMe, it's 35 Gbps. And I think with the introduction of PCI Gen 4 NVMe, that's still going to go up. Now let's talk about networking technologies. What is happening in networking? Sorry. All right. So a little history about networking. In 1982, we were very happy with 10 Mbps network speed when coaxial 1 Mbps Ethernet connections were still the mainstream or were popular. And today we are talking about 100 Gbps or 200 Gbps throughput in the network. In between, what has happened, we evolved from 10 Mbps to 100 Gbps. When it comes to storage technologies, um, to carry storage commands, our protocol was SCSI. The limitation was not network, but the way we carry commands over the network. We are talking about Ethernet. So then in between, we came with the ideas that, okay, let's optimize the transport, the underlying lower level transport. So we came up with fiber channel and other technologies just to optimize the way we carry SCSI commands over the network. But now, since we have our latest NVMe command lines, they can be better used with vast majority of networking, which is available in data centers today. We also call it Ethernet. We'll talk about this in the later slides. All right, so some few more points about networking technologies. Ethernet is the most popular backbone in data centers. And Ethernet carry the underlying traffic. Data centers connected at physical layer are mostly through Ethernet. And then Ethernet carries their traffic or connectivity leveraging, enabling TCP and IP protocols, which are at a higher level, a higher layer. So these are popular technologies. So TCP IP enables how two computers, how two network nodes talk to each other, how they identify, and then how do they unicast, broadcast, or multicast. Then there are other technologies such as RDMA, which is remote direct memory access. Sometimes protocols, layer 3, layer 4, TCP, IP, or even higher level protocols, they have limitations. They're general purpose. They are not purpose built for specific technologies. Then we come up with special technologies such as RDMA, so that our remote access to direct memory is optimized, and hence that's where we get best performance for certain applications like RDMA. So then what is NVMe over Fabric? We talked about it a little bit in the earlier slide. So NVMe is a protocol which enables storage IO commands and then helps flash media to store storage bits. So NVMe commands, they travel between a PCI bus and the storage flash drive. What if we take those NVMe commands over the network, because we have now faster networks available? What if we take those NVMe over Fabric commands over the network from one node to another node? That's what is called NVMe over Fabric. So it's a transport which carries NVMe command over the network. Since networks are high speed, NVMe protocol is optimized to carry huge number of commands, 64,000 storage commands in one queue. And we have 64,000 queues available, and then a lot of cores available to basically assign to those queues. So this gives us very low latency when storage is across the network, when you carry NVMe over Fabric commands across the network. So very low latency and local like performance. The performance is like if you are connected to a local drive. But you're on a network, and then you get the flexibility of remote or network storage, but with the local like performance. This is another look how underlying, like in a typical case, depending upon the protocol, depending on the underlying technologies, things may differ a little bit. But in a typical case, how NVMe in one node inside the node or NVMe over fabric across the node works. So basically, your physical uh, SSDs, they are connected to a physical storage node, as I'm showing on the left side, and then a virtualization layer. For example, there is one from our company called Kumoscale. Virtualization layer takes those NVMe commands from storage, uh, puts them on the network, and they travel over the network so that the other client can utilize it. All right. So when you carry NVMe commands over the network, there are multiple technologies or multiple transports available. Depending upon your current need, you can choose one of them. Um, Most popular is TCP. TCP is a standard in almost every data center. Uh, it's a way of using or it's a way of connecting or carrying traffic for almost everything in the data center or on the internet. Uh, so you don't need anything special. Leverage the underlying technologies, leverage the pre-existing technologies, Ethernet, TCP, and just carry your NVMe over fabric commands from one node to other node. However, TCP is not uh, is not optimized to carry remote direct memory access kind of a protocol. So which basically is what RoCE version 2 is optimized for. So if you want a little bit better performance but are um, ready to add specific hardware, especially NICs, into your servers or clients, then RDMA can bring a better performance for networked storage or for NVMe over fabric storage. All right, so let's see how NVMe over fabric compares to local drive. So in one of the tests, what I did was I tested a local NVMe drive connected to a storage. When I say local, it means local in a storage box or in a server. Um, and then I connected another NVMe over fabric volume over the network to the same node. So, and then compared the performance. So the delta between two block devices, one is local to the server and one coming from the network using NVMe over fabric, um, was very small. Like in case of 4 kilobyte reads, it was 13 microseconds, and in case of 4 kilobyte writes, it was 8. And um, for 128 kilobyte block size, it was around 29 microseconds. So that type of latency uh, is basically negligible. Applications still expect latency to be at milliseconds level or better, although certain applications they go to 3-digit microseconds, but this single digit or 2-digit microsecond delta is negligible. Applications are not going to notice this. So that's the point, that with NVMe over fabric, local performance or the remote performance is the same. So now let's talk about who can leverage such storage and networking technologies. Let's talk about clouds, private clouds, public clouds, especially how orchestration or orchestrator frameworks leverage those technologies. So one such popular framework is Kubernetes. So Kubernetes is basically container orchestration framework. Container is the uh, underlying your workload or a runtime which basically runs your application. So let's look at container orchestration history or container history. In 2008, Linux came up with LXC containers. So containers are basically nothing. It's a group of processes uh, running together in a little isolated way on a server using the same kernel. But with certain privileges, and they are independent from other processes. That's container. So when LXC came in 2008, uh, that was the original concept of containers. And then Docker took it to next level. They released Docker released its image building process and running containers in a much simpler way in 2013. And then in 2015, we saw Kubernetes, how to orchestrate containers, how to run, stop, terminate containers, how to scale containers at a large scale. And then we'll talk about what type of workloads are in Kubernetes. So in 2016, we saw stateful sets in Kubernetes. And in 2019, we saw CSI driver, which is container storage interface driver. It's a process, or it's a way you connect storage to containers. We'll talk about it, how it works. All right, let's talk about workload types in containers, especially in Kubernetes. So there are two types of workloads: stateless and stateful. So when we say stateless workload, so stateless workloads are those workloads who don't require persistent storage. One such example is a web server or an application server. All it needs is a code to run, and it receives a request, it sends a response. If a request is bringing a data, then it passes that data to some other layer, a database layer or a persistent layer. But by itself, it does not store that data. And when it returns data in response to that request, it gets that data from some other layer. So it doesn't have that data. So if you terminate that kind of an application and restart it, it restarts from there because there is no persistence. Uh, on the other hand, stateful applications, they require persistent storage. They save data or they deliver data, right? Some of the examples are databases. So if you terminate them, you need to bring the same storage which they were connected to earlier, so they can resume their work from there. Their stateful applications might be storing terabytes of data. So you need to persist that data. If not persist, you need to find a way to bring that data back, either by connecting the same volume or by synchronizing from somewhere else. All right, so now let's put those things in context. So stateful workloads in Kubernetes, they are mostly used for databases. I'll show you some examples of those databases. They require permanent storage. We already talked about this. So in Kubernetes, permanent storage is provided through persistent volumes. Kubernetes has an object called persistent volume. That's how permanent storage comes to the containers or the pods in Kubernetes. So the stateful persistent volumes, their performance and their flexibility is one of the characteristic based on which you will assign to a pod, or you will decide whether I want to use this or not. So in fact, if we take it to next level, Kubernetes has a concept of storage classes. Depending upon each storage type, where one is going to get persistent volumes from, the storage class can have those parameters. This is my slow storage, this is my faster storage, this is my local storage, remote storage. All those can be into classes, and then containers or pods, they can request volumes from one of those class. So when pod reschedules to a new node, then the storage or the persistent volume travels with it. All right. So let's talk about some of the example applications. MySQL is a database, is a perfect candidate for persistent storage. It needs persistent volume. Cassandra is another database, and then Postgres, MariaDB, which is evolution of MySQL, not an evolution, which is basically nowadays a more popular MySQL. Is MariaDB. That's how I call it. And there are other workloads which need persistent storage. All right. So we talked about Kubernetes stateful applications. We talked about Kubernetes workloads. Now let's see how persistent storage is delivered in Kubernetes. This is through CSI driver, container storage interface drivers. The way container storage interface driver works in Kubernetes is, I'm going to show that in my demo also. There is a central controller which runs in Kubernetes cluster itself. And then there is a node driver which runs on every Kubernetes worker node. So the central controller provisions the storage whenever Kubernetes containers need that storage. It provisions that storage from a provisioner which basically is assigned to that controller, or for which this controller is responsible. Then we get that persistent volume from that storage, and we bind it to persistent volume claim. That's another object in Kubernetes. And persistent volume claim is the one which gets mapped to a pod in Kubernetes. Pod is a set of containers, and it's another object in Kubernetes. You can think about it like from analogy perspective, you can think about it like as a VM, which is basically self-contained identity or entity, a self-contained entity to run a set of applications. In this case, applications run in containers, so pod is a set of containers. Now let's see. When CSI driver connects storage to pods, the storage can be local on that node, or storage can come from network. So let's see the benefits of each of them. If storage is local, you get higher performance because you're not traveling over the network. If the storage is remote, the benefit is you get better flexibility. So for example, if a container or a pod moves from one worker to another worker node in Kubernetes, storage can travel with it. If storage was local, then it cannot travel. Examples of local storage are hard drives, SSDs. Examples of remote storage are fiber channel, iSCSI, EBS, and all that. All right, so putting it all together, this is like how a network storage coming with the help of NVMe over Fabric protocol from one or a cluster of storage nodes to storage clients. This is how it looks like. In case of Kubernetes, for example, on the left side, I'm showing multiple Kubernetes worker nodes. Each worker node is running one or more pod or many pods. Some of those pods may require persistent storage coming as persistent volumes. So that's how it travels from a central storage, how this is how it's connected from a central storage. But All this is done through a provisioning service, through a CSI driver. CSI driver's controller runs in Kubernetes in one place. It acquires, it talks to provisioning service and then gets the needed storage from the central storage or for whatever that CSI driver is written for, and then attaches that storage to Kubernetes containers. So when we are bringing like this NVMe over fabric storage from one central place to each worker node, the benefit of this is that performance does not change. Remember, I showed in one of the earlier slides, I showed how local storage versus network storage, when it's connected through NVMe over fabric protocol, the delta is negligible. So even if the storage is coming from network, performance does not degrade, but you get flexibility. So storage can travel with the pod now. It is not local, so it can travel as the pod travels to another worker nodes. It basically, since the storage is disaggregated, it provides cost benefits. Your utilization is much better than letting some storage go waste in every worker node or every local node. And since storage is at one central place, disaggregated, it's much easier to provide native resiliency if that is needed. Although vast majority of stateful applications which run in Kubernetes, they have native built-in resiliency or a replication. But if you still need it from storage, since it's in a central place, it's much easier to get resiliency from there. So next, I'm going to stop this screen share and come back on this later to finish my last few slides, but I'll switch to demo, a live demo. Let's go to demo. All right, so in this demo, I am basically showing 3 screens. On the leftmost screen, there is a list of volumes provisioned from a central storage. In this case, this is coming from our product called Kumoscale, which is an NVMe over Fabric storage node or a storage cluster. And the top right window shows how my workload is running. Right now, I don't have any demo workload running. I'm going to start one soon. And then below that, there is a list of CSI driver components. There is a controller, only one controller. Since I have 4 worker nodes, 4 Kubernetes nodes, so that each node has its own node driver. Node driver is the one which is responsible to attach, detach central storage to each node. So what I'm going to do is, and below that, I'm just showing how many volumes are connected to each storage node. Right now, worker node 3, 4, and 5, nothing is connected to them because I haven't started the demo. So in the demo, what I'm going to do is I'm going to create a stateful set which will run 3 Cassandra pods. And as those pods start, we will see that the volumes will start to appear in the left window when they are provisioned at the storage central storage location. And then we will also see how they get attached and how those nodes are started. So I'm going to start a demo which is going to create 3 Cassandra pods one by one in a sequence. So the first one started called Cassandra 0. It started on node 3 and it created one volume. Now we see one volume on the left side, and that volume got attached to node 3 because Cassandra 0 is started on node 3. So that's why this volume got attached. It's a block volume. This is an output of NVMe list command, which is coming from Linux shell of this node. So when this node is ready, when this Cassandra 0 is ready, it's going to move to next Cassandra node called Cassandra 1. At that time, we will see that, okay, so it's ready and it moved to that one. And then we see that there is one more volume created in a central storage, and that volume should attach to node 4. So we should see, so this is a continuous watch of command. So it takes like little time, but it's here. So one volume got attached to node 4 because our next Cassandra pod is on node 4. When this pod becomes ready, so when the status changes from false to true, it is ready. So then it will move to the next Cassandra pod called Cassandra-2. At that time, you'll see that there will be another volume created on the central storage node, which is basically being shown on the left side. So on the left side, it's a continuous polling of existing volumes on that central storage node. Okay, now we see that the third volume got created here, and then we should soon see that Cassandra 2 is starting, right? It's starting on node 5. So at the same time, we see that on node 5, we see a volume, a block volume got connected to it. So once all 3 nodes are ready, which soon it will be, what I'm going to do is I'm going to basically move this Cassandra 2 from node 5 to some other node. When it moves, we will see that the volume it is connected to right now also moves. So what we will see is that right now node 5 has one NVMe block device connected. This is a remote NVMe block device. When it moves to another node, it will disappear from here, and one of the other node, wherever it moves, is going to have 2 block volumes, but it's going to be same. It's not going to be recreated, because you can confirm from the left side that there won't be any more volumes, new volumes. So in order to move, what I do basically, what I'm going to do is I have put that move steps in a script. So basically what it is going to do is it's going to first create a simple file on this volume. So this volume, the volume connected to this node, we created a file called while on node 5, so that when it moves to another node, we know that it's the same volume. So it's the same volume, it's not a new volume. So it's now the sample file is created. What we are going to do next is we are going to disable scheduling of future nodes on node 5, so that when we kill this node, when we terminate this node, it does not come back on the same node. Otherwise, there is no point of having this demo. So it should come on different node. How we can prevent is by disabling the scheduling of future node parts on this node. So it's disabled. Now next, it's going to be rescheduled. Cassandra 2 is going to be killed here, terminated here. So it's false, it means it's terminated. So it's now scheduled on node 3, right? So we'll see that node 3 now has 2 pods, 0 and 2, and at the same time, it has 2 block volumes now. The previous volume, which belonged to this 2, was originally connected to node 5. Now it moved from node 5 to node 3. So node 3 has 2 volumes. When it becomes ready, we will see that the file we created while on node 5 still exists. So if it still exists, it means the volume moved with it. And then on the left side, we see that there is no new volume created. So it's not a new volume, it's the same volume which gets moved with the pod as the pod gets scheduled to a new node. So let's wait for this pod to become true. So it's true, it's ready. So now I press an enter, and which is going to do a ls dash L on that volume again. See, so now we have this file. So it means it's the same volume which earlier was on node 5, now on node 3. So Cassandra 2 gets the same volume. So that way our persistence travels with the pod no matter on what node it is. And I have already explained that the performance is, this is a remote storage. We are not compromising on the performance. Performance is like local. So let me stop this terminal share, and I'll move back to my presentation. All right, so we finished a demo, and my demo, a copy is also, I recorded it earlier, and and I put it on my Google Photos, and it's shared there. If you want to play it later, it's available there. Let's talk about some key takeaways. That in case of Kubernetes and network storage using faster or better Ethernet or underlying network, um, stateful applications can be scaled quickly. Right? Keep it simple. So leverage the underlying CSI driver. CSI driver has a controller and node pods. They can automate a lot of work. They are your drivers. Use predefined standards like NVMe over Fabric or RoCE. Right now we are in version 2 if you want to gain better performance. So we also see that performance of network storage is almost same as local storage, although I could not test it for the sake of time, but it stays same. The delta is negligible. Then stateful applications, they natively provide resilience. Most of them leverage that. In case any application does not provide and need it, use it from the storage. So some of the references I used to build these slides, and then that concludes my session. Please take a moment to rate this session. Your feedback is very important, and you can always find me on Twitter or search me on Google or LinkedIn. That concludes our session. Thank you very much. Now we'll open for questions.